Why does Earth support life and maintain a stable temperature over billions of years? The answer does not lie in a single factor, but in a long and complex evolutionary process shaped by the planet itself. Since its formation 4.54 billion years ago, Earth has continuously adjusted, transforming from a molten planet into a system with an atmosphere, oceans, continents, a biosphere, and the first seeds of life emerging from unfamiliar, simple microorganisms. Each time Earth survived a crisis, life advanced one step further. Earth's evolution began from within. From its earliest moments, the planet accumulated an enormous reservoir of internal energy, trapped beneath its young crust. That energy came from two primary sources: heat generated by the violent accretionary impacts during Earth's formation and heat released by the radioactive decay of isotopes such as uranium-238, thorium-232, and potassium-40 long-lasting energy batteries that have operated for billions of years. Today, Earth's inner core still reaches temperatures of roughly 5,000 to 6,000 degrees Celsius, comparable to the surface of the Sunday. Surrounding it is a liquid outer core rich in iron and nickel, in constant motion. This motion generates the dynamo effect, producing a global magnetic field, an invisible shield that protects the atmosphere from solar wind and cosmic radiation. Without this magnetic field, Earth's surface evolution may have ended very early. What matters most is that Earth retained its heat for an exceptionally long time. Roughly half of today's internal heat still comes from radioactive decay. The rest is primordial heat that has not yet fully escaped. Internal energy also drives volcanism, releasing water vapor, CO2, nitrogen, and many other gases, gradually forming a more stable secondary atmosphere. Volcanoes both build new surface and trigger major biological disruptions. Yet on evolutionary timescales, it is precisely these disruptions that force Earth and life itself to adapt. As heat continues to find pathways outward, it activates an even more intricate mechanism: plate tectonics. On the surface, Earth appears solid and stable. In reality, its thin crust is broken into enormous tectonic plates that drift slowly across the hot mantle below, moving at a pace of just a few centimeters per year. So far, Earth remains the only planet in the solar system with active plate tectonics. Its most critical role lies in the deep carbon cycle, a climate-regulating mechanism shaped over evolutionary time. When atmospheric CO2 levels rise, global temperatures increase, heat and rainfall accelerate the weathering of silicate rocks, locking carbon into minerals and transporting it into the oceans. Along convergent plate boundaries, carbon-rich oceanic crust is subducted into the mantle. Tens to hundreds of millions of years later, volcanic activity releases that CO2 back into the atmosphere. Plate tectonics also generates diverse landscapes. Continents, plateaus, and mountain ranges. The Himalayas, formed by the collision of the Indian and Eurasian plates around 50 million years ago, reshaped atmospheric circulation and influenced global climate. On the ocean floor, hydrothermal vents products of tectonic activity supply chemical energy, sustaining ecosystems independent of sunlight and closely resembling the environments where early life may have first emerged. Plate tectonics both creates and destroys. Earthquakes, volcanoes, and tsunamis can erase life on a local scale. Continents erode and are reborn. Ecosystems collapse and give rise to life forms better adapted to new conditions. As tectonic plates continue to drift, collide, and separate, Earth does more than reshape its surface, it evolves as a living system. The oceans become long-term reservoirs of heat, carbon, and biological history. The oceans formed gradually as Earth cooled and water vapor released by volcanoes condensed over the planet's first several hundred million years. Throughout Earth's geological history, roughly 90% of the excess heat caused by radiative imbalance has been absorbed by the oceans. Instead of allowing surface temperatures to swing wildly over short periods, the oceans stretch climate change across thousands to millions of years. This slow accumulation also applies to carbon. Over time, the oceans became the largest carbon reservoir in the surface system, holding roughly 38 trillion tons of dissolved carbon, more than 50 times the amount found in today's atmosphere. Carbon is not locked in place. It is constantly exchanged among the atmosphere, marine life, sediments, and the mantle. As time passed, global ocean currents emerged, redistributing heat and matter from the equator toward the poles. This system is not fixed. It shifts with continental positions, salinity, ice coverage, and atmospheric conditions. As ocean circulation evolves, global climate evolves with it. The oceans do not merely respond to climate, they actively reshape it. While Earth's surface has endured cycles of heat and cold, global glaciations, acid rain, and skies darkened by volcanic dust, the deep ocean has maintained a nearly constant temperature, around 0 to 4 degrees Celsius, for tens of millions of years. This long-term stability turned the oceans into a biological refuge whenever the planet's surface became hostile. It is also here that the earliest traces of life were preserved, with microbial structures dating back more than 3.5 billion years. Ocean sediments accumulate layer by layer over time, storing memories of temperature, atmospheric composition, and mass extinction events through isotopes and microscopic fossils. Without the oceans, planetary evolution would have unfolded too quickly and too violently, leaving life little chance to adapt. But to understand how this long-term memory can be activated or disrupted, we must look upward to the faster evolving system above it, the atmosphere. After the early phases of accretion and outgassing, Earth's primordial atmosphere was dominated by carbon dioxide, methane, nitrogen, and water vapor, with almost no free oxygen. This was a transitional state, appropriate for a young planet at a time when the sun was 25 to 30% weaker than it is today. Under those conditions, life emerged without oxygen, without intense sunlight, existing at microscopic scales. For more than 1.5 billion years, Earth was a planet of anaerobic organisms. They evolved slowly, but continuously, gradually altering the chemistry of the oceans and the atmosphere in ways that were almost impossible to detect over short timescales. Around 2.4 billion years ago, an evolutionary threshold was crossed, the Great Oxidation Event. Oxygen, a byproduct of photosynthesis, accumulated beyond the absorption capacity of oceans and rocks and began to spread into the atmosphere. This was not an immediate improvement, but a planetary crisis. Many anaerobic organisms were wiped out, and ecosystems collapsed on a massive scale. Today, Earth's atmosphere is astonishingly thin and fragile. More than 99% of its mass is confined within a layer less than 30 kilometers thick, compared to the planet's radius of over 6,300 kilometers. Yet this delicate shell is the result of billions of years of biological, geological, and chemical evolution, and it continues to change. The atmosphere is not permanently stable. It is maintained in a state of dynamic balance, where life constantly adjusts its chemical composition through photosynthesis, respiration, and the nitrogen and carbon cycles. When atmospheric composition shifts, the fastest responding system is not the oceans or the deep geology, but the climate, the shortest-term evolutionary mechanism, yet one with immediate planet-wide consequences. Earth's climate has never evolved along a straight line. Instead, It has oscillated continuously, swinging between climatic extremes from worlds tens of degrees Celsius warmer than today to intervals of cold so severe that the planet nearly froze over entirely. Geological records reveal that Earth's climate has repeatedly approached the brink of collapse. Around 720 to 635 million years ago, the planet may have entered a snowball Earth state, when ice covered nearly the entire surface. The reflective power of ice reduced heat absorption, causing cold conditions to reinforce themselves through a positive feedback loop that pushed the climate system toward its limits. By contrast, during super greenhouse periods such as the Cretaceous, climate evolved in the opposite direction. Global average temperatures rose 10 to 14 degrees Celsius above present levels, sea levels climbed by tens of meters, and permanent ice at both poles vanished. These states did not emerge suddenly. They developed over millions of years through the accumulation of CO2, the rearrangement of continents, and shifts in ocean circulation. Climate is shaped by many forces: Earth's orbit and axial tilt, solar radiation, plate tectonics, and atmospheric composition. When climate cools rapidly, habitable environments contract. Organisms are forced to optimize their metabolism, migrate toward refuges, or form new symbiotic relationships. When climate warms abruptly, new ecological niches appear, but oceans acidify, oxygen levels decline, and food webs grow fragile. Each climatic swing is therefore not merely an environmental change, but an evolutionary trial. Seen from space, very few planets manage to preserve conditions suitable for complex life through billions of years of such fluctuations. And it is within these repeated cycles of instability that Earth entered a new phase of its evolution, one in which life no longer merely responds to climate, but begins to act back upon the planet itself. Over hundreds of millions of years, marine organisms such as foraminifera, coccolithophores, and corals have continuously precipitated calcium carbonate, forming thick limestone layers on a continental scale. This is the result of long-term biological repetition, in which carbon is transferred from the oceans and atmosphere into Earth's crust. On land, a similar process occurred during the Carboniferous period, roughly 360 to 300 million years ago. Ancient forests expanded faster than biological decomposition could keep pace, causing large amounts of carbon to be buried as coal. This accumulation reduced atmospheric CO2 levels, driving global climate change and triggering new evolutionary feedbacks. Even soil, the foundation of terrestrial ecosystems, is the product of a long-term biogeological evolutionary process. Microorganisms, fungi, and plant roots gradually broke down bedrock, releasing minerals and forming porous structures that retain water and nutrients. Soil did not appear instantly. It formed over millions of years through interactions between life and rock. At the chemical level, nitrogen-fixing bacteria gradually converted inert N2 gas into biologically usable forms, laying the foundation for global food chains. Sulfur processing microorganisms controlled redox reactions in oceans and sediments, exerting long-term influence on seawater composition and the atmosphere. These processes unfold slowly and almost invisibly, but when accumulated over geological time, they shape how the planet operates. Geological history shows that Earth has repeatedly entered phases of comprehensive restructuring, when the influence of the biosphere reached a threshold large enough to drive changes in climate and ocean chemistry. Accumulated pressures were eventually released through mass extinctions, abrupt climate shifts, or large-scale reorganization of the biosphere. It is precisely during these moments that the system of life was effectively reset, opening pathways for new forms of life to emerge. It is the history of a planet where life gradually became a geological force, evolving alongside geology through billions of years of change. Over the past 540 million years, science has identified 5 major mass extinctions, each wiping out between 70% and more than 90% of all living species. In planetary evolution, these events function as phase transitions, moments when the structure of life is dismantled and reorganized. The late Ordovician extinction, around 440 million years ago, offers an early example of how climate gradually pushed the biosphere toward a critical threshold. As Earth cooled rapidly, ice accumulated at the poles, causing sea levels to fall. Most life at the time depended on shallow seas environments that vanished within a short geological window. Tens of millions of years of evolution were erased. Yet, at the same time, empty ecological niches began to form, opening pathways for new evolutionary directions during the Silurian period. The greatest biological catastrophe in Earth's history occurred at the Permian-Triassic boundary, roughly 252 million years ago. The pressure did not come from a single cause, but from the prolonged accumulation of continent-scale volcanic activity in Siberia. Over hundreds of thousands of years, vast amounts of CO2 and toxic gases were released, driving rapid global warming, widespread ocean deoxygenation, and severe acidification. Ecosystems collapsed in cascading failure. It took nearly 10 million years for the biosphere to recover comparable levels of diversity, but when life returned, it had evolved into a different structure. Reptiles became dominant, laying the foundation for the age of dinosaurs. By the time of the end Cretaceous extinction, 66 million years ago, Earth's evolution revealed a different kind of restructuring, one driven by an instantaneous shock. An asteroid roughly 10 to 12 kilometers in diameter struck the Yucatan Peninsula, releasing enormous energy. Within hours to days, the planet entered a state of chaos. Over months to years, dust and aerosols filled the sky, temperatures plunged, and photosynthesis nearly ceased. Creatures that had dominated for over 150 million years, the dinosaurs, disappeared. Yet, within that evolutionary vacuum, small mammals with rapid adaptive capacity gradually expanded and diversified explosively over the following millions of years. On a planetary scale, extinction does not end evolution. It resets its trajectory, allowing life to continue in a new structural form. In the past, mass extinctions were always triggered by forces external to the biosphere: climate shifts, volcanism, or asteroid impacts. But Earth's evolution is now entering a phase without historical precedent. Throughout Earth's evolutionary history, no species has ever driven planetary change as rapidly as humans. In just a few centuries, we have altered the climate, biological cycles, and global landscapes at a pace far exceeding the tempo of natural evolution. The world's population has grown from roughly 1 billion people in 1800 to more than 8 billion today. Alongside this growth has come an unprecedented expansion of resource extraction, industrialization, and land use change. More than 75% of the planet's ice-free land surface has been transformed by agriculture, urbanization, and infrastructure. Rivers have been dammed, sediment flows altered, reshaping coastlines and downstream ecosystems. These changes are no longer local in nature. They intervene directly in Earth's evolutionary cycles. Many scientists argue that we are now witnessing the onset of a sixth mass extinction, not driven by asteroids or supervolcanoes, but by a single species. What is without precedent is that this agent of change possesses the ability to recognize its own role. Technology has allowed humanity to escape many direct biological pressures: disease, extreme climates, food scarcity, while simultaneously amplifying our impact on the Earth system. For the first time, biological evolution, technological evolution, and planetary evolution are unfolding together at the same moment. Some researchers propose that Earth has entered a new epoch, the Anthropocene, the age of humans. Humanity is no longer merely adapting to Earth. We are forcing Earth to adapt to us. The boundary between a lasting evolutionary turning point and a thin sedimentary layer in the geological record may depend on how humanity understands and responds to this new role. Will we become a stable component of planetary evolution, or the trigger for Earth's next great restructuring? Earth's existence is not a cosmic accident, but the result of a resilient self-regulating process spanning 4.54 billion years. From the interaction of tectonic plates and ocean circulation to the planet's fragile atmosphere, all of these elements have formed a unified biogeochemical system that functions like a living entity. Within that system, life is not merely a passive presence. It acts as an architect, reshaping the chemical composition of the atmosphere and establishing new energy cycles. It is this tightly bound symbiotic relationship that has allowed the planet to maintain a state of dynamic balance amid the harsh fluctuations of space. The Earth we see today stands as evidence of a parallel evolutionary journey. The planet created the conditions for life, and life, in return, shaped a world uniquely capable of enduring within the quiet vastness of the solar system. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.